So VLDLs, or very low density lipoproteins, are again produced in the liver mainly from lipogenesis. So if we remember from a few weeks ago, lipogenesis is an insulin-stimulated process through which excess glucose is converted to fatty acids. These are subsequently esterified into triacylglycerols. And we've seen from our previous discussion that triacylglycerols produced in the smooth ER of the liver are then packaged with cholesterol, phospholipids, and proteins to form a VLDL. The major difference between the VLDL and the chylomicron, again, is their point of origin. So our VLDLs are produced in the liver and will carry our de novo synthesized triacylglycerols. So we'll see that the triacylglycerols in the liver can come from several origins, the first being from plasma-free fatty acids that come into the liver and are reesterified. They can also come from fatty acid synthesis. So this pool of triacylglycerols are not stored in the liver, and these will be our primary source of lipid for our VLDLs. So the VLDL's particles acquire our apoprotein, ApoB100, through an interaction with our enzyme, this microsomal transfer protein. This is also true for the loading of ApoB48 onto chylomicrons. Microsomal transfer protein facilitates that reaction as well. So following the acquisition of our apoprotein, we then begin to load our VLDL particle with our lipids. These particles are then trafficked to the Golgi, just as we looked at earlier, where they undergo several modifications and begin to mature into our nascent VLDL particles, where they're secreted from the liver into circulation. So what you'll notice here that's a little confusing is that insulin will inhibit the production and secretion of VLDLs at two places. First here by the inhibition of ApoB100 synthesis, and then again here at the level of the Golgi. So we're not going to focus on this, as this regulation is fairly complex and, as your text says, not fully understood. So we're going to focus on the aspects of VLDL synthesis and secretion that we do know about. So first of all, there are factors that enhance the synthesis of VLDL production. The first is fed state metabolism. In the fed state, we know that fatty acid synthesis is occurring. Our regulatory enzyme, acetyl-CoA carboxylase for this process, is dephosphorylated and active in the cytosol. So we're synthesizing fatty acids which are subsequently esterified into triacylglycerols. Diets high in carbohydrates, and these will increase our substrates for fatty acid synthesis. Again, excess carbohydrate can be stored as glycogen or used to synthesize fatty acids. So high levels of circulating free fatty acids. If you remember from the previous slide, our pool of triacylglycerols can be generated through two means: uptake of circulating free fatty acids that are then reesterified, or from de novo synthesis. And finally, hormone imbalance. So elevated levels of insulin and low glucagon. And this would again stimulate the synthesis of fatty acids. So if we look at the maturation of our nascent VLDLs once they're secreted from the liver, we'll notice several similarities to chylomicron maturation. So our primary apoprotein on VLDLs is ApoB100, and although it's secreted from the liver with small amounts of E and ApoC2, it also requires an interaction with HDL to acquire ApoC2 and ApoE. So just like chylomicrons, this interaction with HDL is essential. VLDL also interacts with lipoprotein lipase through the ApoC2 protein, and this interaction again stimulates the hydrolysis of our triacylglycerols into free fatty acids and glycerol. These free fatty acids can then be reesterified and stored. So our remaining VLDL remnant, or IDL, has a reduced tag load, as well as it has donated its ApoC2 back to HDL. So it's now characteristic of ApoB100 as well as ApoE. And ApoE will facilitate a reuptake by the liver, where the IDL is metabolized into its primary components. You'll also notice that the IDL can be further metabolized into LDL. This LDL primarily contains cholesterol or cholesterol ester and is largely free of tags. It's donated its ApoE as well as ApoC2 back to HDL and is characteristic of only the ApoB100. This can be taken up through an interaction of both receptors on extrahepatic tissue or through receptors on the liver, and these receptors are specific to the ApoB100. We'll look more specifically at the metabolism of LDL in another week. So now that we know about both fatty acid synthesis and their transport by VLDLs, I'm going to pose this question. So which of the following is not required for the transport of newly synthesized fatty acids to the adipose, to our extrahepatic tissue? So first of all, the interaction with ApoC2 and lipoprotein lipase. If we remember, this is an essential interaction to hydrolyze the triacylglycerols in VLDL particles back into glycerol and free fatty acids. And these fatty acids can then be stored by our extrahepatic tissue. So this is a required interaction. What about the transport of triacylglycerols from the liver using VLDLs? Again, VLDLs are going to be our primary transport of de novo synthesized triacylglycerols in the liver. So this is again a required process. What about the synthesis of triacylglycerols using glycerol 3-phosphate? So this is also a required process. We have talked about fatty acid synthesis, which generates a long-chain fatty acid. And these are then esterified to glycerol to make a triacylglycerol. And that is how we package and move our free fatty acids around as triacylglycerol. So we also require this. That leaves us with D, carnitine to shuttle fatty acids out of the mitochondria. And this process is not part of the transport of newly synthesized fatty acids to the adipose. If we remember, the use of the carnitine shuttle for fatty acids is in the fasted state and moves fatty acids into the mitochondria for the process of beta oxidation. So carnitine is a required component for some aspects of fatty acid metabolism, but it's for the process of beta oxidation, not the process of transport and storage. That's an important distinction between these two processes.